Hi, this video is for Chapter 9, Section 3 in Chemistry, and this deals with limiting reactants and percentage yield. Let's look at our objectives for this lesson. First of all, we're going to describe a method for determining which reactant is a limiting reactant. You're going to calculate the amount in moles or the mass in grams of a product given the amounts in moles or masses in grams of two reactants, one of which will be in excess. And then these two we'll leave for a second video, so we won't cover those here in this first video. We'll get to those in a little bit. Okay, limiting reactants. When a chemical reaction is done, you very seldom, even if you're very careful in the lab, you're never going to get exactly the right amounts of both reactants to react and everything gets completely used up in doing the reaction. Generally, one or the other of the reactants will be in excess. In other words, there'll be a little bit of that one left over, and the other one gets used up first. The one that gets all used up in the reaction is what we call the limiting reactant. Okay, and so it's limiting because when it's all used up, the reaction has to stop. The excess reactant then is the one that there's some of it left over. If you look at this example down here, if you had 5 carbon atoms and 10 oxygen molecules, when you combine these to form carbon dioxide, you would end up forming 5 carbon dioxide molecules, and you would have 5 oxygen molecules left over. In this case, the limiting reactant is the carbon. When that's used up, when all 5 of these carbon atoms react, you can't have any more reactions. And so the oxygen is the reactant that is in excess. Some of it remains after the reaction is done.
In actual chemical reactions, the amounts used of each of the reactants is not so perfectly measured that neither reactant is in excess. Even a slight deviation in mass for one of the reactants can add billions of additional molecules to a reaction system. When the reaction begins, new products form until one of the reactants is used up. This is the limiting reactant. Once it is used up, the reaction stops. We see that the 5 atoms of carbon and 5 molecules of oxygen react to form 5 molecules of carbon dioxide. The remaining molecules of oxygen are excess reactant.
Okay, so if we look at a sample problem here, I'll start with silicon dioxide, which is basically quartz. That's a mineral. That's basically what sand is made out of. It's usually quite unreactive, but reacts readily with hydrogen fluoride according to the following equation. That equation is given for you here. SiO2 plus 4HF yields SiF4 plus 2H2O. In our situation, we're going to look at if we have 6 moles of hydrogen fluoride added to 4.5 moles of silicon dioxide, which is the limiting reactant. And that chart that we used makes this very easy to do. And I will start here by, I will just write the equation SiO2 plus 4HF yields SiF4 plus 2H2O. And of course I'm going to right away put my ratios in down here. And we were told that we have 4.5 moles of silicon dioxide and 6.0 moles of hydrogen fluoride. In that situation, then, which one is the limiting reactant and which one is the excess reactant? You can choose either one of these, either the 4.5 or the 6.0. It doesn't matter. I'm going to choose the 4.5 moles, and for the purposes of this, I'm going to do this one in a red color. What I'm going to do is use this 4.5 divided by 1 is 4.5 times 4 is 18.0. Okay, and I'm just using the table the way we would normally use it. Divide down, so 4.5 divided by 1. Now I'm going up, so times 4 gives me 18.0. What that tells me is in order to use all 4.5 moles of this silicon dioxide, I need at least 18 moles of hydrogen fluoride. Do I have that? And the answer to that question here is no, I do not have 18 moles, I only have 6. So what that tells me is that this is the limiting reactant right here. The HF is the limiting reactant. I'm going to run out of space here, so I'll just abbreviate. The hydrogen fluoride is the limiting reactant. Now, I'm going to erase that, and let me run it the other way. Let me start with the 6. If I start with the 6 moles, divided by 4 is 1.5, times 1 is 1.5 moles. In order to use all 6 moles of the hydrogen fluoride, all I need is 1.5 moles of the silicon dioxide. Do I have that? Yes, I do. Alright, so either way you do this, it tells me that hydrogen fluoride is the limiting reactant and SiO2 is in excess. Okay, and these problems are, now this one was a very simple one because we were just using moles. When you have masses, it's very similar. You have to work down and work back up and then ask yourself the same questions. Just compare the two numbers that you get. Let's take a look at another example dealing with the synthesis of water that we've dealt with before. You have your formula equation here, H2O plus O2 yields H2O, and then the balance equation, 2H2 plus O2 yields 2H2O. And so I've put that equation down in here into our chart, and we're starting with 7 moles of hydrogen. So we'll 7.0 moles of hydrogen, and we're going to react that with 5.0 moles of oxygen. And again, we want to figure out which one is the limiting reactant. So we'll put in our ratios here, and let's again, you can choose either one. Let's choose the this one right here, 7. 7 divided by 2 is 3.5, times 1 is 3.5. Do we have 3.5 moles here? Yes, we do. We have more than enough of that. So that tells us that the H2 is the limiting reactant. Okay, and then obviously that means that O2 is the excess. Reactant. Okay, when we're all done with this equation, all of the hydrogen will be used up. There will be some oxygen left over. And again, had we done this the other way, we would have started with 5 divided by 1 is 5 times 2 is 10. We don't have 10 moles of hydrogen, and so we would know that the H2 is the limiting reactant. Okay, so it doesn't matter which one you choose, which one you start with. You can get the correct answer in this regardless. Okay, we're going to look now at an example using masses to do the limiting reactant. And so we're going to use this example here. The black oxide of iron, which occurs in nature as magnetite, can be made in a laboratory by reacting hot iron with steam. according to the reaction that's given. And I've written that equation below in the table so that we're all ready to go with this. We're told in part A here, when 36 grams of water is mixed with 67 grams of iron, which is the limiting reactant. Okay, so let's start with 67.0 grams of iron and 36.0 grams of water. Notice that in this particular instance, you've got to be careful. You can't just take the 36 and write it down here with the iron. You've got to go in the correct column. So just pay kind of close attention to that. All right, and I'm going to also write my my ratios down here and get that taken care of. And now we're almost ready to go. What we're going to have to do is start with either iron or water and work down and come back up. So we're going to need both formula masses, both the formula mass for iron and for water. The formula mass for iron, if you look in your periodic table, is 55.845, and as a formula mass that's grams per mole. Okay, it's actually molar mass. And for water, I don't know if you remember a while back I told you write this number down because you're going to need it. This is one of those times when you're going to need it. 18.0153 grams per mole. So by having that number written down, we just saved ourselves from having to do the calculation. Alright, now I'm going to start with the water, just to be different. I'm going to start there at the 36.0 grams, and I'm going to work down that column and then back up the iron column to see how much iron would I need to completely react with the water. Okay, so we'll take 36.0 divided by 18.0153, and we're going to divide that by 4. And so now we're down at the bottom here, so now we're going to start going up the iron column. So I'm going to multiply by 3, and then I'm going to multiply by 58.845. And I get 83.69, and I get 83.7 to 2 sig figs grams. Alright, now I can compare this. In order to react 36 grams of water completely, I would need 83.7 grams of iron. Do I have that much iron available? And the answer is no, I don't. That means that our limiting reactant will be the iron. That's the limiting reactant, and so that is the one that I have to use for calculations. And you can see that this was no different from the other calculations. You know, when we were doing with moles, we just have to include the formula masses. So what I'm going to do, I'm going to cross out that 36.0 grams because I want to just remember that I cannot use that in subsequent calculations. Okay, so in the second part of this problem, we're being asked what mass in grams of black iron oxide is produced. That means I want to find this number right here. And you can see that I'm going to have to start from the mass under iron, work down that column, and then come back up the iron oxide column. Well, that means I'm going to need the formula mass for iron oxide. So let's calculate that real quick. We're going to have 3 times iron, which is 55.845, and we're going to have 4 oxygens, which is 15.9994. That gives me 167.54 for the grams of iron, and I have taken into account significant figures there, so I've lost, I had to round that number, and this one gives me 63.9976. We're going to add those two together, and I get 231.5376. Alright, now when we're doing addition subtraction, we have to round to the column of the leftmost last significant figure. That would be this 4. So I'm going to have to round this to 2 decimal places. So I'm going to report that number up here as 231.54 grams per mole. Alright, and now I'm ready to do my calculations. So I take the 67.0 divided by 55.845 divided by 3 times 1, which doesn't do anything, times 231.54. And I get 92.5966 something. I have to round that to 3 sig figs because we started our mass of iron was only 3 sig figs. It's been all multiplication and division. So we round at the end, and I'll round that to 92.6 grams. So my answer here is 92.6 grams Fe3 SO4. And remember, when you're reporting a number of grams of something, you got to tell me grams of what. So this is not just 92.6 grams, but 92.6 grams Fe3 SO4. That will do it for this part of chapter 9-3.